Doppler effect. We must have noticed often how the sound of an ambulance's siren seems to change as it approaches us and then passes away. A similar phenomenon may be observed with the sound of an approaching train's horn. As it passes away, the sound of the horn seems to change. If we pay attention to the sound as it changes, we observe that the actual change occurs in the pitch of the sound. We notice that the sound of an approaching train's horn seems to have a higher frequency as compared to the sound made by the same train as it moves away from you. This apparent change in frequency observed in moving objects is known as Doppler effect. It is named after Johann Christian Doppler, one of the first scientists to study this effect. Buys Ballot, another scientist, tested this experimentally in the year 1845. Doppler effect holds true not just for sound waves, but also for electromagnetic waves.
Using Huygens principle. Refraction of a plane wave. In this section we shall learn how to construct a model of a refracting wave using Huygens method and prove Snell's law of refraction. Let's consider a plane wavefront AB incident on the boundary PP' separating air, medium 1, and glass, medium 2, as shown in the animation. Let AB be a crest. Let the angle of incidence equal I. Let V1 and V2 be the velocities of the wavefront in medium 1 and 2 respectively. Let the time taken by the end B of the wavefront to reach the boundary be t. Therefore, BC equals V1t. As distance traveled equals speed into time taken. End A of the wavefront would travel to E in this same time t. The distance traveled by A equals velocity in medium 2 into time taken equals V2t. Therefore, according to Huygens principle, we can draw a spherical wavelet of radius V2t and draw a tangent EC to the wavelet passing through point C. EC is the refracted wavefront. From triangles ABC and CEA, sin I equals BC by AC equals V1t by AC. Sin R equals AE plus AC equals V2t by AC. That is, sin I by sin R equals V1 by V2. That is, sin R V1 equals sin I V2. If light travels with a velocity v in a medium of refractive index n, then n equals c by v, where c is the velocity of light in vacuum. If n1 and n2 are refractive indices of media 1 and 2 respectively, then v1 equals c by n1 and v2 equals c by n2. Therefore, we can write c sin r by n1 equals c sin I by n2. That is, sin r by n1 equals sin I by n2. That is, n1 sin I equals n2 sin r. This is known as Snell's law of refraction. As BC and AE are two successive crests, as the wave propagates, BC is the wavelength of light in medium 1. Let us call it lambda 1. AE is the wavelength in medium 2. Let's call it lambda 2. Therefore, BC by AE equals lambda 1 by lambda 2 equals V1t by V2t equals V1 by V2. Or V1 by lambda 1 equals V2 by lambda 2. This implies that if the velocity of light decreases when traveling from a rarer to a denser medium, V2 less than V1, its wavelength also decreases and vice versa without any change in frequency. The above derivation also shows that if R is less than I, then V2 is less than V1. As in our example, R less than I, it is obvious that V2 less than V1. Similarly, the plane wavefront will behave in the same way when it travels from air, rarer medium, to water, denser medium. Note that the incident wavefront is a series of points in phase with each other. As these points reach the boundary, each point behaves as a source and sends out spherical wavelets. The common tangent to all these secondary wavelets is the refracted wave. Note that the plane wave changes direction as it leaves medium 1 and enters medium 2, for example water. We can see that the wave turns toward the normal to the boundary when it enters the second medium. The photograph shows an HENE laser beam entering a transparent cuboid filled with water and emerging out. Observe how the beam changes its direction. Surface. In this section, we shall describe reflection of a plane wave at a plane surface and prove Snell's law using wave model. AB is a plane wavefront incident on a plane refracting surface MN. It is reflected and travels in the opposite direction as CE as shown in the schematic diagram. Let the time taken for the point B to travel to point C equal t and the speed of the wavefront be v. Therefore, the distance traveled BC equals Vt, as distance traveled equals speed into time taken. BC equals Vt. As the wavefront travels in the same medium, the speed does not change. Hence, the distance traveled by end A in this time t will also be Vt. In the diagram, this distance traveled equals AE equals Vt, AE equals Vt. In triangle ABC, sin I equals BC by AC equals Vt by AC. In triangle AEC, sin R equals AE by AC equals Vt by AC. That is, sin I equals sin R. That is, the angle of incidence is equal to the angle of reflection. This is Snell's law of reflection. As the distance traveled AE by point A after reflection equals distance traveled BC before reflection equals Vt, by using Huygens principle, we can locate the position of A after reflection by drawing a sphere of radius BC equals Vt with center at A and a tangent from C. These two meet at the point E. Thus, CE is the reflected wavefront. We shall see how a plane wave gets its shape changed during refraction in a triangular prism and lenses. When a plane wavefront is incident on a transparent triangular prism of a denser medium as shown in the visual, the bottommost part of the wavefront enters the denser medium earlier than other parts. Hence, it travels slowest. Hence, the wavefront emerging out from the other side of the prism is tilted. When a plane wavefront enters a thin converging lens, convex lens, its middle part enters the lens first and travels most slowly. Hence, when emerging out from the lens, this part is the least traveled in comparison to other parts. Hence, the refracted wavefront is spherical in shape with convergence toward the lens as shown in the illustration. Due to the same reason, the plane wavefront acquires a spherical shape after refraction. As the wavefront travels, it converges to the principal focus of the lens. When a plane wavefront is incident on a concave mirror, it acquires a spherical shape and converges to the principal focus of the mirror, as illustrated in the schematic diagram. A plane wavefront changes its shape during refraction depending upon the refracting medium and the shape of the reflecting surface. In any refraction, total time taken by light from the object point to the image point is always the same, whatever path the ray may take. In a converging lens, the ray at the center is slowest, but covers shortest distance, whereas the rays at top and bottom ends cover largest distance but travel fastest. Thus, all the rays take the same time to begin from the object point to the image point. Light. Consider a star A present somewhere in outer space. Suppose light waves from this star reach our Earth. If the star A is stationary, all waves take the same time to reach the Earth. On the other hand, if the star moves away, waves which emerge from it later travel longer distances than the earlier ones. Hence, the time taken by them is larger. In other words, their frequency is less. This means that the waves are stretched out, that is, the wavelength is larger. In the visible light spectrum, red light has the longest wavelength. Therefore, when the wavelength of any light wave increases, it is shifting towards the red region. This shift in frequency is called the red shift. If the star moved towards the observer, the waves which emerge later travel shorter distances than the earlier ones. Hence, the time taken by them is lesser. In other words, their frequency is high. This means that the waves are compressed, that is, their wavelength is smaller. In the visible light spectrum, blue light has a shorter wavelength. Therefore, when the wavelength of any light wave decreases, it is shifting towards the blue region. This shift in frequency is called the blue shift. Hence, in case of light waves, Doppler effect causes a change in color of the incoming light. When the source moves away, the decrease in frequency is given as fractional frequency and is expressed as delta V by V. The fractional frequency and c, the velocity of light in vacuum, bear the relationship delta V by V equals minus V radial by c, where V radial is the component of the velocity of the source along the line joining the source and the observer. When the source moves away from the observer, V radial is considered to be positive. This equation holds true only in cases where the source velocity is far less than c. In other cases, the derivation requires the application of Einstein's special theory of relativity. Doppler effect is the basis on which astronomers measure radial velocities of distant galaxies and other extraterrestrial objects.